Okay. Given that the subject incorporates real time, shall we start on time?
I think you can start, yeah.
Okay. So this is actually very interesting. I mean, I used to study, and I had a here, right? So I sit mostly over there and think over there. So this is quite interesting for me to. I mean, I was a TA before, but doing a lecture is something else. Okay. So hi, and very welcome to this talk about architecture of a real-time data distribution platform. It's quite a longer talk, but one thing which I would like you to do is also, if you have questions in between, don't hesitate, right, to raise your hand, and we can also take a question right then and there. So for me, you don't need to wait until the end of the talk. So before we go into the interesting parts, as custom, something short about myself. So I'm a senior consultant at U1. You can find our booth directly over there if you want to talk to us after this talk as well. So we are a consulting company based in Zurich and in Athens, specializing in all things data, like mostly data warehousing, but analyzing data, machine learning, basically everything that touches data. So not so much software engineering, mostly data engineering, data science, machine learning. Before that, I worked with startups, also in Zurich and in Berlin. So this is my largest company so far. Let's see how it goes. Okay, and at D1, I am one of the tech leads in one of the larger projects which we have, which is back, I guess. Ooh, sweet. Okay, and that's why I got the pleasure to talk to you, because like what we learned from this particular large project, I will show to you today. It's basically just a showcase of this architecture, or learnings, a little bit of recommendations, what me personally think will work, and stuff that will not work. So a little bit about my background. I mean, I studied neuroscience, machine learning, software engineering, and now I'm mostly also doing software and system architecture, like enterprise architecture. But if you want to talk to me, you can also definitely talk to me about gardening and fermentation. So if you have questions about this, I'm also very happy to answer these type of questions. Let's see. Okay, so today there will be roughly 4 parts. The first one is general eventing. What does it mean with sending events, like business events, a package over the internet, and how to process it, and what you need to pay attention to when you do that. Then the architecture, where we're displaying the architecture that we have implemented, or what you would recommend in doing in the future. Then, how do we operate it? Right, so we're monitoring, alerting, all of these things. And then some takeaways. All right. Now, before we start with with interesting parts, another short interlude. So what is the aim of this platform? So the idea is not to distribute data as fast as you can from point A to B, right? So it's not a point-to-point connection that we want to facilitate. We want to allow that some producers send data to a lot of consumers, right? So distribute it over the whole world. So think about it. All right. Okay. Let's see. So we have some couple of goals which you optimize, or which you want to optimize, right? So and there are like 3 parts of this. So the first one is latency. And you want to minimize latency. When latency is the time that something, that message takes from A to B, right? And what we want to achieve is roughly 200 milliseconds from end to end, meaning that when a sensor sends data, when maybe he does some things before that, but we don't care about that. Basically, as soon as we provide a sensor with data, it passes through our system, and then it arrives at the end. So imagine that you are in a room, in a bar, with a friends of yours, right? And there's a football match going on, right? And you want to be alerted if there's a goal, right? So as soon as the goal hits, 200 milliseconds later, you should receive a push notification on your phone, which is actually quite fast. So think about it like, so the networking from EU West to North America takes, if you have a direct connection, can take like 80 milliseconds. If it's in the same networking zone, so like if you have a very, very fast connection, you can be like with 250 microseconds. But this is then super fast direct connection. So since most of the data which we collect, or in this case collect, right, there's not in a nice data center, right? So this is real-world data, real-world sensors, which send us data, and they're positioned everywhere. So we have no super tight control of the cable quality that you get or the direct connection. The second thing that we want to optimize is throughput. And here the goal is to do like roughly 1 terabyte per hour. Which might seem at the beginning a lot, but I mean, if you're downloading stuff at home, it does not take you, I mean, to download like a good movie of good quality, it does not take you like an hour to download it, right?
Sorry, I think the screen just started again.
Yeah, so what can we do? Okay, yeah, let's see. Maybe I need to stop a couple of times. And then the third part that you want to optimize, or which is a requirement that we need to deal with, is this delivery guarantees. So here the aim is to deliver the data exactly once. And there are some mechanisms which you need to follow in order this to happen, because it's a distributed network. Basically, you need to wait until you get an acknowledgement that the data was received and stored and processed. And this is surprisingly difficult in a distributed way. Why this is difficult, we can explain that maybe in the questions section, but this will not be part here. There are basically, for these delivery guarantees in the industry, there's minimum ones, right, exactly ones, and maximum ones. And I say like here the aim is, right, because you can never guarantee exactly once, and I don't care what people tell you, in the real world, it's just not feasible, right? But this is the aim that you try to do. All right, then the second disclaimer which I want to bring in, it will be mostly boring, I would say, because there will be nothing fancy, right? There's no generative AI, there's nothing new, cool, hot technology which will be in there. There's no genius idea which I'm going to present to you. So it's basically just a little bit of plain software engineering, right? How to apply best practices to a problem which you face, make the right decisions, and then take it up from there, right? So nothing which you come up with, my mind is blown away. No, this will be more like, okay, I've seen this, cool, maybe I learned something from it. All right, now, without further ado, let's start with part one. So, part one, and so like this is the basics of eventing, right? So we have a source which sends us some data, it triggers an action somewhere, and then the action sends something else, again, probably like an event, to a sink, right? So the action, the beginning, a goal was detected, and then this information needs to be transferred somewhere, and someone else triggers a notification. Can also trigger multiple notifications, right? And usually people talk, I even have a very invisible, all right. So usually people, when they talk about eventing, they say, right, it's only the source and an action that is required, but since we want to distribute data, this is very important to highlight, and this is basically what we build everything on top of. So let's make a little bit more concrete example. So imagine you have this ball, right, and this ball transmits its location. So it has this very nice data structure which is sensed, right? So obviously each message has a unique ID, right? It has a type, it has a time, which is hopefully in this format, and this is the only format allowed. And then it has a data. So this is also, like, if you want to know a little bit more about this data format, cloud events is where you should look this up. Because all of these, like the format of data, how you messages, that is not very well defined in the industry. Everybody does what they want to do. So this is what we have, right? So now imagine we have this arrangement of a sports thing, call it a pitch, right? And we have a ball in the middle of it. And then the ball will move over time, right? So these are the positions which are recorded. So like the darker it gets, like the more future in time you go, right? And then the end of it, this is what should be displayed, right? So this is the action that you should want to display. So then that was a goal after all of these actions taken. So let's take one step back and make it a little bit easier to visualize and to understand. So let's assume, right, that the x-axis is the long axis, kind of, right? And like, so if it touches -1, or like it's close to -1, it should be in the goal. Very broad simplification, but I think it illustrates a point. So this is the trajectory of the data which we get. So the first thing which we need to, which we will see, right, is that the distance on the x-axis here, right, the t, the time it's not uniform, right? So if you make an assumption when you develop your algorithms that the data which you're receiving, that you get them exactly at this precise moment in time, every day, right, every time, it will not be the case, right? So you will have some distance between when you receive the data. Because it can very well be that the data was sent regularly, right? But due to some weird networking stuff going on, there's some delay. So this is something which your algorithms need to deal with. But let's imagine, right, furthermore, that sometimes you get weird mistakes like this, right? So the blue one, that is the ground truth, where the ball actually was at that point in time, but you get the red one. Then how do you deal with these type of errors? Because like at that moment in time, right, it will already indicate that the ball was in the goal, but it is a mistake, right? It's not true. And then the question is, how do you deal with this type of question, this problem? Right? Either you discard it through some other data points that you have, let's say the speed, the accuracy, not the accuracy, like the acceleration that it receives, right? And it's like, okay, based on these values, it cannot be there because no human possibly can kick a ball that strong, right, that it would reach this point in time. Or you wait a little bit, right, until you get the second entry point here, and then you say, it can also not be, right? So like it cannot travel this trajectory. This is also impossible. So there are some ways how you can deal with that. There is no clearly defined way of how you deal with this because this is very application specific. But basically, you need to make sure that you check for errors and handle them, if you can actually. So let's look at one other option which is also very common. I'm not saying and this happens all the time, right? Physical sensors are never as accurate as you want them to be, and your data vendor will never tell you how inaccurate they are. So huge learning here, right? Never trust them. So let's say you get like this, and if you kind of like compare from before, something is weird, right? So these points have changed. And to illustrate this point a little bit better, let's imagine these are like this is the order of the events, the ground truth, and also like how they were measured. And these are like in the green and the red, we see like two scenarios of how the data could be received. So in the green one, right, there's just a huge delay, fine. It will still impact on the data which I can then produce and which I can show people, right? But the impact is still kind of manageable. But the red one is actually more what you will experience in the real world, right? You get messages twice, and you get them out of order, and data is missing. Right? And you need to be able to handle all of these cases. And I'm saying like all of these cases, right, it's a lot of stuff that you need to take care of, and then a good technology choice allows you to deal with these errors in a nice way. So basically, when we look at single stream difficulties, it's not a problem, right? It's a difficulty which we need to deal with. So we have these two types, at least in my opinion, right? One is the sensor difficulty, and one is streaming difficulties. So with sensor, it's mostly error detection and error handling, which is not as straightforward. It's like either you have a model which automatically fixes bad data, which you completely trust, right? Or you do like a finite aggregation period, like a sliding window over which you aggregate the position or fix in between some points, right? But then there comes some problems, like how long do you wait until you close the window? What happens if data arrives out of order or out of window? So all of these considerations you need to take and to deal with. Then the second one is extreme difficulties. So in here, the largest one is clearly arrival order. It can either be out of order, right? But it can also be out of window. So when you have an aggregation, you want to report, for example, you have a football match, and you want to show like how many passes occurred in the first 15 minutes, right? How long do you wait until you tell people, yeah, it got like 5 passes? But then new data comes in. Do you correct it, or do you leave with your old value? So these are all questions which it's not that much engineering related, right? This is business. Business needs to make a decision. As your application maker, you need to make this decision. So in my eyes, if you want to design something, if you want to work in real-time applications in distributed fashion, there are a couple of requirements which you need to take into consideration. So one is obviously sense of order, which boils down to that you need to have good timestamps. Because if a good timestamps that comes from the sensor, you can always reorder. It can also be an auto-increasing ID or something, right? Always incremental, fine. I would still like to have a timestamp, but if it's not feasible, because it's not every time it's feasible that you actually have that, you still need to get some sort of order. And if you don't have it, then how you deal with that becomes much more complicated. You need to have a clear definition of what does mean too late. So when do you discard this data? Or when do you finish your calculation? I mean, when you do a credit card transaction in the Migo, right, you hold it against the machine, right, and then like a second or so later, tops, the machine ever says you accept it or deny it. Do you want to wait a minute? The customer, no, that's completely, no, right, it will not work. You need to make a decision right then and there. And then your applications, they need to follow this idempotent receiver pattern, which basically means that if you receive the data again, you need to be able to deal with that. Either you discard it, or you say, okay, I've seen it again, or you do some internal updates and then publish it. Right? And then you need to take also care of these offsets, basically of the data which you have received and the data which you have sent out, in case something crashes in between. Maybe it's your application which needs to restart. Maybe it's someone else that needs to be able to reread past messages. So these are the things which you need to take care of when you do your application design. I mean, this is all very simple, right? I feel like there's nothing, again, this is not nothing fundamentally new here, but yeah, not everybody understands this, I think. So now let's talk a little bit about the part 2, the architecture. And here I wanted to impress you with a cool zoom in and zoom out thing, but it didn't work, so you have to split it up. So this is the full architecture. I will highlight then specific parts in more detail, but generally this is what we do. So on the left side we have our data providers, right? And in the middle we have basically what this platform does and how we operate it. And then here on the right side we have our data consumers. One interesting and very important thing to mention, it's not necessarily that each provider only provides data, right? They also consume data, obviously, and send it back. So there's this circle, right, of things that you need to take care of. But it makes the diagram much more complicated, so let me stick with that. So generally, right, so there's the data providers, data consumers, and in between we have these the 5 layers, kind of, right? So on the top we have this operational layer. He makes sure that things are running, and that there are alerts and metrics and all of these things that are kind of reported. Then we have the ingress layer, right, which is like the input layer. So, but this is our input layer, because sometimes maybe we need to pull data from somewhere, or we need to make slight modifications to it. Then the ingress layer pushes data into the transport and storage layer, right, which is like mostly what now we're talking about will be this message queue, right, using Kafka. Here we also have 2 other data parts where we store data. One is an operational database, and one is an analytical database. Basically meaning this is very fast, right? And this can take lots of data, but it's also much slower and much more expensive. It has historical data and all the data that you ever need. But in here, we try to be very, very fast. And there's this clearly need to make this distinction, because otherwise it will not scale. And then the transport and storage layer will either send or pull the data, right, from the compute layer. And there we have like a stream processing, which is Flink. We have a streaming monitoring, which is also Flink. And we have an ETL pipeline, which is done with dbt. No.
And this time it doesn't.
Wait, because my screen, no, that's my laptop that went into sleep mode. All right. Too long on one slide, I guess. So here I split up these 2 parts if we do with Flink, because one is basically only interesting for us as the operators of this platform. One has an impact on the actual consumer, right, where we actually transform the streams of data which we get. Then we have this egress layer, which is basically just how do we send data out. Obviously, the streaming API is basically this one here, right? The REST API done with pgrest is basically this data here, and then the analytical access is basically the Snowflake on top. I mean, I'm not sure if everybody here knows what Snowflake is and Kafka is. We will go into this a little bit more detail, but basically Snowflake is just a huge fancy database that companies really love. Same with Power BI, it's a fancy tool to make charts. Yeah, should.
What's ETL?
It's extract, transform, and load. It's basically just like how a pipeline for normal data pipelines. Put like ETL here because it's this standard way of processing batch data. We do a lot of batch transformation also in Flink, right? But with DBT, you can, when you have a data vault, data mart, like lots of views and tables, then it gets a little bit unmanageable. And then when DBT comes in. DBT is a nice tool, can highly recommend. Okay, so now let's zoom into a little bit of these.
I think you have another question.
Yeah, sure.
I'm also getting familiar with InfluxDB.
Yes?
According to this chart, in which...
Prometheus. Prometheus.
Oh.
I can highly recommend InfluxDB. Very fond of it.
Exactly. Exactly, because I have worked with Snowflake and other ones, and I want to kind of integrate, so I can ask you later. So.
Yeah, sure. I mean, yeah, let's do this later. I'm not sure like how you want to integrate them, but we can discuss it later. All right, so let's now zoom in. If it works. No, I guess it does not. Give me 1 sec. Ooh, okay, now I guess. All right. So here is data providers, right? And here I listed like 3 types of technologies which we have, or how we ingest data. So, right, so there's this webhook, where basically people send us data through an HTTP port. We have a TCP connection because some vendors, they are, I mean, either they are old, they are not wanting to update, or they still think that TCP is the best technology to send data with the internet, and you need to deal with them. Right, and then if you have, then you have basically like sane people who I really enjoy. They provide you like a Kafka endpoint, and you can get the data from there. Basically, the goal of this part of the layer is that you get the data, and you ensure that you received all the data. So you try to be as simple as you can here. Right, you want to reconnect if crashes, but no logic whatsoever. Right, so no transformations, no fancy stuff. Right, basically you count the messages you received, and that's it. With Kafka, right, this is easily done. There's an offset. Basically, you can go to the Kafka server and tell it, give me the data past this point in time, and it will send you the data again. With TCP, yeah, good luck if they have set up the server, but then you need to handle the weird implementation of the custom TCP server, which sucks. With the webhook, it's even worse, because like they send you data. Do you know if you received it? I mean, I guess. So, obviously, right, there is no good way to do this. If you plan to do this on your own or kind of, right, push everybody to Kafka or RabbitMQ or any other queue, message queue that we have. There are a lot of things out there. Now, let's talk a little bit about this transport and storage layer. So as mentioned before, right, we have these 3 parts. One is super fast, medium fast, and one is very, very slow. Obviously, data needs to move from one section to the other rather fluidly, but only basically in this direction, right? There's no way that some data from a very slow database, right, moves again back to Kafka. It's like, why would you do that? It makes no sense. No one is entering this data, changing the data, right? So basically, people have either the way of sending events or sending like more batch-oriented data, and then this data flows into this analytical database. Sure. So most vendors, they store the data themselves, right? So you can, if your server crashes, you can call them later on, say, can you send me the data again? And they will snap at you and tell you, like, why didn't you store it yourself? Usually it's the case, but not every data provider can do that. For example, there are some, let's say, sensors which provide a lot of data. Way too much, so that basically they don't even store the raw data streams themselves. They store the more processed or compacted data, and this you have access later. But you need to store everything which they send you. So basically what we have on Kafka, right, we have 2 streams. One goes directly into like an archival blob storage kind of, right? And then one is which gets processed. So we always have access to everything which they send us. It's also important to legal issues, right? Because usually you're with a vendor, you sign a contract. You send me this amount of data with this quality in this amount of time. And if they don't do that, right, then you need to tell them, that you show them, right, hey, you didn't send me this data, and we didn't receive this data, and then the whole legal thing starts going. So yeah, we store the data in multiple places. lots of times, basically, right, in multiple various stages throughout the full flow of the data. How you do that, right? How is efficient? I mean, basically, it boils down that you want to enforce a data storage format which is sensible, which is not JSON, but people really like JSON. But something like Avro or PK, right? Something like this would make more sense. But generally, storage is very cheap, so no one cares, right? I mean, in general, like good software engineering these days is mostly about what is cheaper, and your time as a developer is much more expensive than storage. Okay. Now let's enhance this, right, with the compute layer. So we have this transport layer, and here I want to talk a little bit about how we organize our Kafka topics, because it was brought up some time back, and how this data flows here. So we have this message queue, and we have multiple topics, right? And usually they are like business key kind of or stream key oriented. That means like if we get one data provider, they get their own Kafka topic, right? So that is very flexible. So all the data, all the formats is in this one topic. However, sometimes it's not that easy to do because like maybe there's no easy grouping, or you have a lot of different formats which you need to save. So how do you do it then? Basically, we have one topic to rule them all, like this MISC kind of topic, right? Where we store everything, and then somewhere in the payload, there's the type. People can then cast it without any issues. Then the operational database has something similar, right? Multiple views, multiple tables, nothing fancy. And the analytical database we're not even talking about today. And of course, there's this huge interconnection between the stream processing, the stream monitoring, and the compute and storage layer, right? I mean, Flink, Apache Flink, is a platform, a framework, which reads from Kafka and multiple sources, right, and can join them very efficiently. I mean, that's why we picked it. You will see a little bit more later. But basically, this is how this whole communication kind of works. So there's a lot of connections. And then at the end of the day, we report it to either data producers or consumers. And here again, it's important to note that most of the time, the data will not flow very easily in one direction, right? Maybe there's, at a later stage, someone receives detects an error, right? And then you need to send something back again, and then you need to process data again. So there's usually this cycle, and it gets very difficult to draw. That's why I didn't really... Man. All right. I didn't have this. Right, okay. So now let's a little bit about these technologies which we are using. So as you might or might not know by now, I really like Apache Flink. It is basically the heart of how we do our processing. It comes with a lot of things directly out of the box which you can use very easily. It will help you also with defining and programming your applications. So one, for example, is the snapshotting and offset management. Basically, the outcome is you have nice delivery guarantees. So Flink itself, right, if your programming crashes, if you wrote it in a conform way, right, it will restart, it will reread the data or resend the data if your database which you send data to, or the HTTP which server didn't give you like an OK, right, it will resend the data or recompute the data, and it will also do this somewhat intelligently, right? So it's not plainly rereading all the data. And it comes also with a lot of common stream operations like windowing, aggregations. How do you define also your application? But it helps you with defining this language and going with this. So highly recommend. It's also very fast in stream operation. So like they make this advertisement as one of the low latency, high throughput technologies out there. Very, very, right? So 5 out of 5 would recommend doing. People usually then ask me like, hey, what about Spark? Spark also can do streaming. And no, it can't. People tell you they can, but it does micro-batching. So there's no way how you can really do low latency. If you are fine with these micro-batches, right, good, okay. But then don't tell me that you're doing low latency, high throughput kind of scenarios, right? Because you don't, right? You don't need to. And then one last advice. Don't try to write your own streaming framework. I mean, we tried. I think like this is kind of like the curse when you come from a good university and you have a nice engineering degree, you think you get smart and you also have the time to do that. In reality, you mostly don't. Yeah, sometimes you need to do this, right? Because like maybe Flink doesn't do it. Because Flink, for example, cannot really work well with a webhook because an HTTP, a long pole connection, does not really tend to be working well in a distributed fashion. Then you need to work something on your own, right? But then you need to integrate all the things which Flink does for you, right? Or which basically is required here. So, would not recommend writing on your own. We also employ Apache NiFi, which is mostly part of our legacy pipelines, which is mostly for simple routing and extraction of data. Right? So if you very, very simple, very, very basics. And my biggest think of it is it only has a GUI. Right? So if you're a fan of GUIs, drag and drop using a mouse, maybe. Right? It's very fast to get, to say like a float, this is what I define it, right? To get something running, it's very hard to maintain because it's a GUI. How do you maintain it? How do you do testing with it, right? It's very difficult to do all of these stuff. 2 out of 5, would not recommend. Then this last layer which we have on our API, I just mentioned it here because it's a very nice technology and I want to promote it a little bit, as all the others as well. We're using Postgres, right? To define, it allows you to define views directly on the database, which we then can easily export as an HTTP server, right? So for me, this is by far the easiest backend I ever created because I have a database. I need to have a database for sure, right? And then with PGREST, I have my server as well, and then I can formulate these queries. Easily done, right? So there's no more, I don't need to put like a Spring server, all of that stuff, Flask, no, why? You still need to have like a server, I say, on top, right? For rate limitation, access control, all of these things. But usually, right, you have this anyway, and this is then further out on your application, right? Often you also integrate it with other tools. I mean, if you deploy it, let's say, on AWS or Azure, right? They come with a tool which basically allow you to do this, and it does the routing. And then, but you don't need to have a Spring server underneath that does this. 6 out of 5, would strongly recommend. So then the last part of this architecture is this operational layer. And here we have these 4 parts. We have logs, we have metrics, we have the orchestrator, and we have our manual intervention tool. So logs, here we're using Splunk. We're using Splunk because in this case, our client, they really liked it. Right? They already have a license. But you can also use something else, right, in the Elk stack to do this for you. With metrics, we're using Prometheus and Grafana to display them also in real time and do alerting there. Oh, again, nothing fancy, right? Industry standard. For the orchestrator, we call it orchestrator because it's Airflow, right? It does a little bit more than just like a basic think like Airflow stuff, right? It's not the data pipelines, but using Airflow, we have a lot of automation. Basically, is taking care of this. And then the last part, which is this, we call the manual intervention tool, is how do we intervene if data goes wrong? Usually there's an expectation, right? You call the data provider, hey, there was something wrong with your data. Can you please fix it? But in this case, we're talking about real-world data and also real-world events. So you cannot wait. It's like, yeah, we'll fix it tomorrow. So, yeah, but I need this to fix data now. Right? My state is broken. So you need to define how you intervene. This needs to be a clear set of definitions and how you do it. All right, chill. So Apache Airflow is what we're going to use, what we are using there, right? And it's this heart of our automation and orchestration. It's how we define when to scale our systems, right? And it basically has this direct control through Kubernetes of all of our deployments. So we talk directly through Airflow to the Kube API, right? And tell it, hey, scale that server, scale this deployment. You can now shut down this other thing, right, and scale it up. It can also talk to other HTTP APIs to our more managed services, right, for which we have no direct control. I would say it's a very complex technology, right? The documentation could be better. 3 out of 5. It can do what it does, right, and it's basically the industry standard. I don't really know why, because it's a beast to maintain, to operate, and to work with. Then Prometheus and Grafana, it's basically the de facto standard of how you do metrics and alerts. It can also do logs, right? It can display data from multiple sources, like from your database, from an APP, HTTP port. Lots of different stuff that you can do there, right? Definitely recommend. If you ever set something up, everyone tells you something, hey, we want to have alerts and metrics, and they tell you to do something else, they need to have a very, very good reason to not use Grafana and Prometheus. Splunk, right? It can do a lot, but it can't do everything. One thing that really annoyed me is that joining logs and metrics is surprisingly difficult and limited. So something that I think should be a given if you want to have a log aggregation and like metrics kind of system. You have metrics and you have logs, right? You need to be able to merge them, and you really can't. It is super expensive, crazy expensive. Cannot recommend at all. But if you can afford it, yeah, sure, go for it. Mostly it's like big enterprises that like it, right? But even then, it gets super expensive. So let's say there are some other tools out there, right, which can do this for you, which are open source, and basically do the same. All right, so now onto this part 3. How do we operate it? Because again, the architecture is very simple, right? Like there's not that much there, but it really does the trick. And the biggest thing that we need to do here, right, is scaling. How do we scale? Because if you have multiple matches at the same time, or multiple events happen at the same time, right, or like more consumers are now interested in this one right now, right, but maybe not tomorrow. How do we scale with that? So one big thing is obviously we need to make a right choice of technology, right, something that can scale. We also, from a design perspective, the compute needs to be distributed. And applications need to also be designed for horizontal scaling. So like I can deploy multiple of you, right, to be able to handle the load. If I cannot do that, right, then I'm in big trouble. And we also need to have multiple caching layers. So all of this is basically not displayed, right, but the caching is basically on the API outbound layer, right, or basically Kafka does it, right? Kafka does the caching and also like how it sends out the data. But like the server does it, right? And then basically everything that we run either is a managed service, so basically we pay, in this case Azure, for it, or it runs on Kubernetes, which basically means it can scale, because like we implemented it correctly, right? It can scale very easily. But there's one thing which is difficult. Zalando, for example, right? Also, they have something similar, right? In order to handle all the transactions which people do, but they can scale on basically based on the amount of messages in the queue. We cannot do that because if we scale, then we are too late. Then messages are already waiting in the queue. Then they will increase the latency. So basically, for us, we need to do this 4 times. So we cannot react just in time, right? We need to do this beforehand. So basically what we do is we have a prefix scaling depending on the importance of an event. So before we go in that, right, we determine, hey, how many people will we potentially have? And then we scale it. And then inside of the, let's say, the event, right, there are small adjustments which need to be taken, which you can do. But generally, everything needs to be done before you go, because we cannot really fail. Then things that we monitor, right? So we don't monitor data quality per se. We're not interested in if the sensor is wrong or if it's faulty, right? We also are not the judge of it. We are a data distribution platform. So we distribute data to lots of people, then some other team does this check, then sends the corrected data to us. We facilitate this, maybe by offering them compute or helping them with programming it, or we program it on our own. But basically, they're not interested in data quality. So we measure our ingress. There we measure like how much data goes in, right? The arrival of some specific events. And for the egress, we measure mostly like the consumer lag. So how much are other people behind when they consume from our Kafka service? And if they get super well behind, basically we call them up and tell them, now you're like 3 minutes late. Everything okay on your end? And this obviously happens in an automated way, right? Through another message on a Kafka topic. And then at the system level, of course, like performance, API response time, and we introduce latency. Because if it goes above like the normal flow, then something is phishing. We need to do investigations. So here, there's only like a couple of pictures, but this is basically one of our dashboards which we have. So when we go into one of these events, like this match, right, we have these 3 phases: pre, during, and post-match. And on top, basically, you see a couple of special events which need to be there. So like when we receive them, that's green, all good. And then here we measure a little bit like the performance of the data, of the flow of the data in the blue part. And then the red part is basically the post-processed data. If it's concatenated, everything's looking good. So let's look at one example, which I think is very interesting. So basically what you see here is a little bit the game time from multiple phases. Like say that like a tennis ball goes in a tennis match. I don't know. I mean, it has like 6 sometimes. I don't know. I don't play tennis, right? But soccer, right? I mean, you have the 2 normal phases. Ice hockey, you have 3, right? This is basically how we display it, and then you can display this timestamp from multiple sources, which are now quite important. Then here we have this, and this is basically the most important graph, which is this alignment of the multiple feeds. Because we have multiple feeds, right? Usually you have a sensor data, multiple sensor data, which you may or might not need to join yourself, right? Let's say that you have multiple camera feeds, looking like in tennis, looking at the ball, you need to join these feeds. And then or like server sensor data or human data, and you need to be able to merge them, join them, and this is basically the difference between. So if it if the difference is maximum 1 second, right, we're still kind of okay. If it's larger than that, we are in problem. And then, like if this goes out, right, then a message is getting sent out, and people can complain. So if these sometimes, right, the state in this platform reaches a point of no return, so to say, where it cannot autocorrect itself, where you need to intervene. So for this, we wrote a custom program. It is not a difficult program. It needs to be, it gets triggered through Airflow, right, so that we can give it to someone else, because me as a consultant, my hours are very expensive for the client. So of course, we give it to a support company, right, which then clicks a button. But it is always manually triggered, but it needs to be foolproof, right? Like if they send the wrong data at the wrong point in time, yeah, right, so there needs to be some corrections. So basically what it does, it injects special messages into the queues to fix the state. Like, a streaming processing, right, is usually like if a state and you have an event, you merge these two and you produce either a new event or a new state. And basically with this, we can do it. Of course, right, this needs to be communicated verbally and also automatically, right, through the system. So we have a notification hub, which we also send this data across company. So multiple companies, right? Every vendor and every producer is part of the system, right, to automate the systems. If they want to participate, good. If they don't want to, then they don't want to. But basically, this is always a verbal thing. This makes monitoring and operations like this also quite intense, right? Because you get an alert, okay, you fire up your laptop, right? You look at the graphs, you look a little bit, and then someone calls you up, okay, now we need to intervene. And then they do it. And then magically, the statistics are working again. But it's not that much magic, right? It's at the end of the day, simple injection of a couple of specific messages. And with that, we go a little bit to the part 4, like the takeaways. And so one thing which I want to point out here is this reality check. Like, when I started doing this, it was very... I had these big dreams of doing like test-driven development and all of the cool stuff, but basically that's not happening here. Especially in the world of streaming and event time, it's very difficult to test because basically what you need to do, right? You need to replay an all recording of data, right, in the exact time that you received it. And then even then it's only one recording, right? Then that's fixed, it's deterministic. But usually the real world is not deterministic, right? There's a lot of nuances, variables which you cannot control, which change how everything works. And you need to be able to validate it and test this. And basically you can't, right? So you need to trust that your applications are good, but then you also can simulate this. There's also lots of different teams and companies involved, right? I mean, can you simulate with the data vendor sending you data? I mean, you can ask them, hey, can you send me some more data? But maybe their simulation is not as truthful as they would like it to be, right? Does it really reflect the real-world event, right? I mean, you have a tennis match, and then suddenly someone runs across the field, right? How will this then be shown in the sensor data or the event data which you have? I'm pretty sure there's no simulation which does this for you from the vendor, right? So again, right, it's time-sensitive and probabilistic by nature. And a stream system testing framework would, I think, in my eyes, would make a very good thesis to work on, right? Because there's nothing out there, just wink. Would be very happy to see like a new open source tool which will allow me to do this in a better way than what we have created. Then the another thing is that this tooling and these frameworks, they are not defined. So there's this from the Cloud Native Foundation. There's Cloud Events, which is a project to harmonize how events are packaged. Like what is the format? But because so far everybody basically did whatever they like. So if you then compare this to databases, right? Databases, this is a standard. There's no wiggle room. You need to connect your application to a database. Okay, chill. I know exactly what to do. But with all the streaming stuff, no. So it's always changing, and there's always something new out there. Kind of like JavaScript, but even a little bit worse. So the libraries and the frameworks, right, they're still changing, still evolving. But since there's not that much, let's say, pressure, actually, right, to actually do this, but who really needs real time? Very small amount of applications actually need to happen in real time. Most of the time, you can get by with setting up a Postgres database and sending the data, or like scaling the Postgres database. There's a huge degree of reliability required in this case, right? So like your application cannot crash, right? Which you need to be able to handle this. So this is there's no margin for error during an event, right? I mean, let's say, right, you have a finale of a tennis match, right? And then exactly at the best moment in time, right? I mean, your system application crashes. It will look very badly for you and your employer, right? So these are all things which make it very, very difficult. So basically what you then need to do, right, you have a lot of unused resources most of the time, right? Scaling, you deploy like your machines on a much larger VM than necessary, which costs money. You scale up your infrastructure, which costs money. You implement a lot of features to help you in very specific edge cases. And making this decision also is very difficult, like where is this additional amount of time and investment here? So here, one needs to be very, very careful and also needs to think this very, very much through to the end. And then big companies, they're also like stable and boring technologies, right? So like you want to pick something that is tested, like Kafka, right? Kafka is a tested application, right? There's some other cool messaging queue applications out there as well that you could pick, but mostly you don't want to do that, right? And there's also highly likely no CI/CD. And the main reason here is there's no margin for error, right? So there cannot be like, maybe your automated testing didn't capture this one particular case, and let's say you deploy it during an event, and this application crashes. I mean, you don't want to have that responsibility on you. So basically, there's a huge amount of code trees, right? And then you need to figure out how you do validate it and test this. How do you introduce new things into your system? Actually becomes a huge challenge if you have that low amount of margin for error. Okay, and much faster than anticipated, but yeah. So the takeaways, right, for me would be you start simple, right? Then you keep it simple. And if you can make it simple, then make it more simple. You choose a boring technology which has been proven to work well. And what I would really recommend is to have an automated cross-system communication and status sharing. If your application crashes, it's very helpful if you tell others that your application crashed, because then they can correspond in time. Or let's say, right, you receive a lot of, like, the data quality is not good enough, right, and you want to report a little bit more extreme statistics, like, today Rafael Nadal, he's not hitting as strong as he used to, right, because you measured this, you inferred this from the data, and you want to display this because there has an impact on betting and also people who enjoy the sport, and like statistics. But then you have this problem that what happens if this data is wrong, right? You cannot produce something faulty. So you need to make sure that it is truthful. And this, if you do automate it, that a system is crashing, that you detect like an error, then other people can react instantaneously. If you need to reach out to them over Slack, hey, or call them up, hey, something is wrong with the data, much too slow. And then the last bit is you need to get the data formats right from the get-go, because otherwise you will have to deal with lots of weird formats. And there's only one datetime format, and his name is ISO 8601. Extended is also allowed, but that's it. No other datetime format allowed. You can also do Unix timestamp. I'm also okay with that, but everything else, no way. And if people tell you otherwise, you can give them my number or something. Okay, and with that, thank you. And working for D1, the booth is there. If you want to talk more, like him here, but also later on. Thank you.
So I hope that this time it works. Okay, last time it didn't. No, it still doesn't work. Amazing. Okay, so thanks you for this very exciting talk, and we have about 7-ish to 10 minutes of questions. So if you have questions, then
I have a question that's more on the data distributors. So how exactly does this technology work? So when you have a soccer game, for example, they can track exactly how many passes there were and where the ball is in each second. So do they have cameras everywhere that's tracking it with a visual algorithm?
So usually these data providers, as of today, most of them provide more like raw data. They specialize in raw data, so not passes. They sometimes try to do that, but mostly it's raw data. There is one company, Kinexon. They're famous for the sensor in the ball. I think they also do it in the NFL right now and in various football. FIFA, for example, does it. Then Hawkeye is also very famous for camera-oriented tracking of data. So they have 7 to 15 cameras around the stadiums, usually high up, and they track everything. They also do the limb tracking, somewhat accurate, I would say. There is also CryEnHigo. They have more flexible camera system installed. Also do like computer vision basically based tracking. Then there is also Genie Sports in the UK. They have a new fancy Dragon system, they call it. Lots of multiple small cameras connected over Wi-Fi, and again, visual. So most of the tracking is done visually. Tennis, right, is also done visually, so that there's cameras, right, which track it. And there's not that much sensor data. I think like now in football, people want to introduce like wearables, electronics in it to track it, or like put electronics in the foot. But most of it is done visually, so for a computer vision process. And then again, like the aggregations, which they do then on top, let's say pass detection or something, is actually surprisingly difficult. I mean, if you have a ball and you have some sensor of acceleration, they can map it, but they can detect an additional force was acted on it. And I know that because like it's a very small story. I got it from the people from Kinexon. We know them. So during the World Cup in Qatar, there was this one point where one footballer, he jumped, right, and from the screen, from the video, it looked like he would have touched the ball. The ball, like with his head, right, he touched the ball fell down, then into the goal. Then they looked at the sensor data, and they realized, hey, during this point, like during this couple of frames where he could have touched the ball, no further force was acted on the ball itself. So he did not touch the ball. So later on, he lost the goal counted to him because they could detect, no, he did in fact not touch a ball. Maybe he scraped it with his hair, but that's not enough. So introducing the sensors in it is very challenging. For example, like how do you distribute the data then out? So for Kinexon, they have multiple sensors which they collected. Basically, they have a distribution kind of thing inside of a ball. Then through radio wave triangulation, they find out where the ball was and do the timestamp on it as well. But it's very difficult to transport this data because a lot of data, how do you get it efficiently and safely out? Also, if you have a sensor in the ball, it's how do you make sure that it is, again, round? Yeah, sorry. Something else? Sure.
How would you recommend starting out and getting into these technologies like Kubernetes and these Apache frameworks?
I would say, I mean, if you have a Raspberry Pi and a couple of sensors, right, is actually to start with something like this, right? I mean, you can start up a Kafka somewhere else. It doesn't need to be distributed, right? I mean, we distribute it, but there's a need for it. You can install it on your home server and then send data to this Kafka. I mean, a Kafka is not necessarily for real-time purposes, right? It's also like if you want to have a queue of data which you want to process. Flink, and then I would start with Flink. Flink is surprisingly easy to work with and get the ball rolling there. I would say like start with something that you fully control. I mean, there's also some APIs which you can scrape, let's say like Yahoo financial data, right, which is still, I think, for free if you take the delay, right? Basically, you need to find a data source which provides you data in a streaming way so that you can put some stream processing on top of it. And then find a good use case, right, that you think is valuable for you in the end of the day. There are a lot of things that you can do, but yeah, I think like you need to find a source of data that you want to aggregate, display over time. Right? Maybe it's, I don't know, number of trams that arrive in time or not in time. I don't know. All right.
All right. I think we have time for one final question.
Shoot.
Yeah. So I was just wondering when you group messages for this maybe data, do you do this in the SQL database or do you do this within the
In memory. In memory in Flink.
Okay.
We do it everything, all we do there in memory, it's in Flink, and we also have a couple of windows there, right? Basically, we decided to republish data if we get the error correction. And then we let the consumers decide how they want to handle this. Because we are, again, right, we are this distribution platform, so we cannot make this judgment call for them, how they should interact with this data. This all needs to happen in memory. So basically, we have these group data that have a time to live, right? And this is, I think, a day or so, right? And if then data arrives after a day still belonging to the same group, yeah, okay, then it doesn't get updated, then we discard it. But everything like this happens in memory. Of course, everything then is stored also in Snowflake. So then later on, then there's another layer of autocorrection on top of it. So like that, then the analytical database should display always the truthful data, no matter how late it arrived. But we cannot do this in time, in real time in Flink. There's just no way. All right. I guess, thank you for attending. If you have more questions, I'm still here. Otherwise, have a nice afternoon.